I guess it also answers the question. My question is the number of times a bolt rotates in a screw linear to the length of that screw? If I were to make a guess, or rather a hypothesis, I would say that if the length of the screw increases, the number of full rotations a bolt makes to be fully screwed into that screw will increase as well. So, it seems pretty simple, right? All I have to do is count the number of rotations a bolt makes and then note that down beside the length of the screw. And then I can later analyze that data. I do have a few concerns, but I'm going to run some tests to see if they're valid or not. So what I have here with me is the smallest screw I own, which is a 0.375 inch screw, as well as a compatible hex nut. I've gone ahead of time and colored in one of the sides red, so I'll be able to see every time that rotates back around. So I'm just going to go ahead and get that in on the top and then start counting. So that's one rotation, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes around a bit. So I don't exactly know how far around that went, and that was one of the concerns I had initially, is not being able to accurately measure decimal values. So like if it doesn't make a full rotation around the screw, I'm not gonna be able to tell if that's like 0.5, 0.1, 0.2, so on. So unfortunately, I do not have a drill that counts rotations, and in fact, I don't even know if such a drill exists. But on the bright side, I do have a motor with a built-in encoder. And an encoder is a device that counts exactly the number of rotations it has. The trouble is I have no way of attaching this screw, the screw head, to the motor. What goes into the motor is something like this, which is an axle. And as you can see, the top of this axle and the top of the screw head, they don't join. So an option is to 3D print a connector between them, but a connector would have to be extremely precise, and I don't have a 3D model that precise. So I think the better solution would be to use hot glue to make a 3D mold, kind of like a housing for both of them. That way, when the axle rotates, the screw will rotate with it. So, here is the result of that. It's an axle that has a heading taped on that will be able to attach to a screw. If I bring the screw that we just had over here, we can now see that if I attach it correctly, the screw is attached to the head and rotates with it. If a bolt is now attached onto the top of it, when the axle rotates, it'll screw in the screw. It'll screw in the bolt. And similarly, we will attach this to the motor, and which will count the number of revolutions that this axle makes, in turn calculating the number of times this bolt rotates. So this is the setup. Bolt attached to screw, screw attached to axle, axle attached to motor, motor attached to brain. When the system is powered on, the motor will spin this axle while I hold this bolt in place, effectively screwing the bolt in. It'll then also read out the number of rotations that this motor has performed on the axle. That will be the number of rotations our bolt makes. So with that, let's get into the experiment. So that's it. Users experience over 1 hour of experimentation in under 2 minutes through the power of editing. So here are the results. Now all that's left to do is plot them and then analyze the data. So this is how it looks if you graph it. All the points are plotted, and there is a line of best fit to match. We have a very strong linear relation here, which is backed up by an r-squared value of 1. So a few things are clear immediately. First of all, this is definitely a linear relationship. We can see a clear straight line and an r-squared value of 1. This is a very strong linear relationship. The next thing we see that this is a positive correlation / upward trend, thus proving my hypothesis correct. This is because when x increases, y increases as well, and in this case, x is the length of the screw and y is the number of rotations a bolt has to make to be fully screwed in. So that proves the original statement of if the length of the screw increases, then the number of rotations a nut will make increases as well. So taking the slope from the equation derived from the line of best fit gives us 31.9x. That means in real life, for every inch a screw gets taller, a nut makes 31.9 more rotations. Then, taking the y-intercept, we get a problem. A y-intercept of negative 1.88 does not make sense. That means that when a screw has a height of 0, a nut makes negative 1.88 rotations. So in other words, when there are no screws, nuts rotate 1.88 times backwards. Of course, that makes no sense. It is an effect of several factors that I could not control during the experiment, despite my best efforts, which led to an error. Due to things like friction, slip, encoder misreadings, and my own human error, the numbers are not exact. We however did get quite close. Negative 1.88 is not far from 0, which is what it should have been. Oh, and here's a line that's parallel to mine, some interpolation and some extrapolation. But why? What was the point of all of this? People usually complain that math has no real-world applications. I think I have an example that can prove that wrong. So, how can this information help in real life? Well, as our world moves further towards robotics and automation, robots, such as the ones that assemble cars, are becoming more prevalent and commonplace. This information can be useful to them. Say it is assembling a laptop. It needs to know how many times to rotate a screw so that it does not over-torque and split the metal, and so that it's not too loose. Perhaps that can be calculated knowing this equation. It's pretty exciting that a math project might be used to help robots assemble millions of things. I think this is yet another example of how we find math all around us in the things we use the most. Thanks for watching. I hope you enjoyed the video.